Cool, thank you. Okay, let me maximize this. Let me know if the resolution and everything is clear, just in case. The slide is like loading for me. Yeah, I hope the slide is clear. Okay, good. Thank you, guys. Okay, so welcome. Good to see everyone. So welcome to this session about the prerequisite crash course. Before we go into it, let me just recap, especially for the ones joining us. I know we have some new users from what I can see. Essentially, this is where we started. So this is now completed. We call it Module 1, also known as the Foundation module. We started from, very basics, really, naive set theory and a bit of group theory. Then we went to rings, blah, 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 complex vector spaces, blah, 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 until we got into actual, Hilbert spaces stuff. So from a mathematical point of view, this is really like, it's essentially very algebraic. So in particular, this is like, from a quantum mechanical point of view, we are just dealing with the finite dimensional Hilbert spaces. However, you got exposed to a bit of group theory here, and also in the matrix group section, which then brought me to ask these questions, or at least have a wish list for what could make sense for Module 2. So for me, it was really three things. First, Module 2 has to be, it has to cover a little bit more advanced mathematics than the foundation module, right? Second, ideally, it should be closer to the algebraic topics covered in the foundation module, right? We cover a lot of, I guess, group theory in particular. So that's one of the things that I had in consideration. The third thing was it has to be something versatile enough, relevant to not just mathematics, but to other applied topics, mathematical physics, quantum computing, and other stuff. Okay, so that actually was exactly after scratching my head for some time, and I think I already floated this idea with some of you guys, that it would probably make sense to, module 2 to be about Lie theory, in particular Lie groups, Lie algebras, and their representations. I will get back to this in a minute. Just as a thing of a motivation, I will just share some few stuff just to keep you motivated why you should study Lie groups. I was a bit lazy, and also I didn't want it to come from myself, so I did a bit of digging online, a bit of help from Google to see what people are saying. I found this is very interesting applications on the thing on the Stack Overflow about the applications of Lie theory. You can see there's a bunch of stuff in mathematics that the subject has influence in, including algebraic topology, for instance. For those guys on the audience, the physicist, gauge theory, standard model, if you are not with the, you don't have group theory, in this case Lie theory, Lie groups, you're not going to be any far from understanding the thing, let alone creating a new theory, right? So yeah, so that's one motivation. Another one, especially for the quantum computing guys, one of my LinkedIn connections, this Professor Arthur Ismailov, he's interested in applications of quantum chemistry. quantum computing into chemistry and these things. So one of the papers I saw last year, end of last year, something he was talking about was to do with the variational quantum eigensolvers. This is one of the popular things that people are trying to find useful stuff with the existing NISQ devices. The current generation of quantum computers are, not that powerful. They're very noisy, and these things. The question that a lot of people are asking is whether you can do something with it. And variational quantum eigensolvers are some of the approaches, stuff that people are trying to do with it. So he has some. So I definitely recommend you to have a look at this. So the connection is this thing here, this thing called Baker-Campbell-Hausdorff. This is something that you will learn about in the Lie theory section, but this is definitely this is part of the thing. It's within the scope of the topic. So for a bit of motivation for the quantum computing guys, there's also some of his lectures on the thing where he talks about some of the algebras that he's using on the thing in his research across different things that he does. So I definitely recommend following his YouTube channel, watch some of his lectures. Another thing, not just quantum stuff, deep learning. Here's an interesting paper called Deep Learning on Lie groups. You can have a look at it on the thing. Just Google the title, you will see it. It's actually, it has a very high citation in these things. This is essentially part of a wider movement of something, some of you might know, called geometric deep learning. So there you go. I hope this gives you a bit of a flavor, or at least some motivation. I didn't have time to find more. And actually, one of the things that I will do as we go through the Lie stuff is I will start inviting people for webinars, people, applying the theory into their research, whether physicists, and other parts of science and engineering. So that's one of the things that I will emphasize. And by then, hopefully in the first few weeks of the session, you will have enough understanding about the subject. So that way, when I invite people for a webinar, you are not going to be lost. So that's the plan. So what's Lie group anyway, for example? So here's a thing of Wikipedia. It says in mathematics, a Lie group is pronounced Lie. Well, you already know, is a group. You know what a group is. But then it says it is also a differentiable manifold. Okay, so it's not just a group. It has another structure. It has a topological, geometric structure that that's called a differentiable manifold. Actually, if we wanted to make a bit of fuss, we will say a smooth manifold, but that doesn't matter at the moment anyway. So when we get to the top, to the actual module, you will know what all this means. So my motivation for the prerequisite is, instead of starting, waiting until we start and then come up with what differentiable manifold is for you. The idea is to give you like a crash course on manifolds, only relevant stuff. So when we get to the Lie side of things, we're not like starting from scratch, and also, you have enough time to observe the stuff. So that's the idea behind this crash course stuff, summer crash course. Okay. So in a nutshell, this is more or less how things look like. So before we even talk about differentiable manifolds, you need to talk about topological spaces. Okay. So topological spaces are the higher, the abstract things that's higher up there. And then inside them, you have topological manifolds. So topological manifolds are special type of topological spaces. And then within topological manifolds, you have these guys, these differentiable manifolds. For us, we will take smooth and differentiable to mean the same thing. So this is what we need. Okay, so this crash course idea is to get you from here to here to here, but without, at least in this for the moment, for the purpose of the crash course, we won't dive deeper into these things. Just what you need in order to pick up the stuff, the minimal knowledge for you to be able to build the to follow the Lee theory stuff. Okay. So I will be very surgical in this. However, the reference materials, for the thing that I will share with you in a moment, in a few minutes, will have enough content for you. If you want to dive deeper before we reach, before we start the second module on your own time, for your own, like doing self-study, you are more than free to do that. And even after the module, some of the reference materials will stay there forever, because it's a massive, manifolds. These guys here, the theory around them is like is very massive. So there are so many things that we simply cannot cover. I mean, we can cover, but not in. It won't be feasible to cover it like in space of maybe 3 months or so that I have planned. So yeah. So I'll be very surgical in this, very disciplined to just go with what you need on topological spaces in order to understand what topological manifold is and so on. So that's the plan. Let me check the chat. So someone is asking if this will be uploaded on YouTube. Yes, the thing will be uploaded on YouTube later. Yeah. Okay, so before I move on, let me try to see if Soham is also available, because it would be nice to have his feedback. I still cannot find our friend Soham. That's interesting. So I'll come back again. Yeah. So that's the idea. So for you to understand what we need, we need to start with topological spaces and topological manifolds, and then go to these guys here. This is what we need, because as the definition says here, a Lie group is a group. You guys, you already know what a group is. At least if you have taken the foundation module, you know what a group is. So, but what you don't know. I know some of you will probably, especially the Sohams, the guys in the advanced, in physics, graduate guys will know what a manifold is. So, but I assume most of you will not know this. So it's an opportunity for you to learn about these things. Okay. So here's a plan. So the plan is on the, I forgot to put the date here, so apologies for that. I will follow up. So the plan is to start on the 25th of June. I believe that's a Friday, okay? And then the plan is to go through throughout July, perhaps the second or the third week of July. In this section here, I will try, my objective is to not have more than 2 sessions per topic here, so we're not wasting too much time on anything, because we'll come back to manifolds later, how manifolds and the group structure are connected, in the context of the Lie stuff. We'll come to them again. So we'll come back to manifolds again. This will not be the end of it. So, we don't want to waste too much time. So I'm thinking like not more than 2. If I can do each of them in 1 session, I'll do it. But if it's like, if the session, I will see. It depends on what I want to cover and, how long I think the slides, how lengthy the slides are and so on. So, but I will try to stick no more than 2 sessions per thing here. Okay. So we'll start with point set topology, really. So this is like, the most abstract topology, really, on sets, right? Or the plain or the boring topology, if you will. And then we'll move on to metric spaces, because we need to define, in order to talk about manifolds, we need the so-called standard topology or Euclidean topology, as some people call it. What all that means, you will know that in the thing as we go through. Okay, so after metric spaces, then we'll go through topological manifolds, and then the final thing we will cover is these guys, differentiable manifolds. So you know what these guys, this means. So the objective is really for you to know what this is in this part. And then we will move on sometime in August, perhaps the second week of August. This will be very brief. So, you know, we're going to cover Lie algebra. So we need to, we need to know what an algebra is. There's a formal definition of what algebras are. You guys, you already, the ones who are like, those of you, I assume most of you have taken the foundation module, already know what the rings, you know, what the vector space is. And so this will not be a problem. This also will not be a problem because, you know, we will just give a flavor of representation theory in the abstract group theoretic sense. So it won't be like there's nothing to connect with the Lie, really. So the Lie aspect of this will come later. So just to give you a flavor of, you know, a bit of representation theory on an abstract group. Okay, so after that, hopefully before the end of August, then we should have, you should have a little bit of time to kind of, you know, wrap your head around these things before we start with the module. In terms of this time frame, I think, let me go back again to the slide. I was planning to start in like the second week of September, but I think it's probably better to start in October. And then, you know, by December we should wrap it up, and maybe we can start thinking about module 3, for instance. Okay. In that, actually, I will ask on the audience here, especially the ones right now, what do you think about starting in September versus starting in October? I guess I can ask, you know, who is okay with October from the guys alive online here? Okay, so there's more Octobers, depends how we do it. Is asking George. I mean, the difference between October and September is not really much. It's like 2 weeks. So the earliest, if it was September, the earliest I could start is probably the second week of September. So whereas with this one, with this, as I'm putting it here, it would be like in the first week of October. So let's see, first week of October, where is this? So that will be on Friday, October the 1st. So the first day of the month itself. On Friday, yeah. And actually, I'm also flexible. You know, I know we've been doing the sessions on Fridays, but I'm also flexible on Tuesdays. So it might be the case if you guys, at least the majority, are happy with Tuesday too. We could, you know, maybe switch to Tuesday, or if we have some extra, like, you know, a situation where maybe we want to cover more than what we wanted to initially cover, there could be an option where we do, you know, some weeks we do double sessions. We do Friday and then Tuesday. But anyway, this is something to sort out as we go along. You know, so it's not a problem. Default, let's say Fridays. Are Fridays okay for most of you? And also the time is the old time, like 5 p.m. UK time, okay for most of you, especially our friends from India? Okay. Yeah, okay, cool. So, okay, so let me get back to where I was. Here, yeah, okay, so now, before, I'm pretty sure there's typo somewhere, but you guys, you already know me, so so apologies in advance to the new new attendees. I'm known as Mr. Typo. So yeah, anyway, this is a prerequisite I will need you to wrap your head around. This is essentially just before the crash course, okay? So before June the 25th, you need some basic set theoretic concept, really, Okay, so we are not wasting time going through, set theory stuff. We already covered some of this stuff in the first lecture, and there's also like a material like this. If you go to the courses GitHub repository, you will see this test book and these pages. This should cover all these guys, these things, these concepts that we need to get started, like the power set, intersections, unions, Cartesian product, blah, 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 indexing. This is very important because all this will show up in the definition of what a topology is on a set. Maps, the notions of pre-image of a map, composition of maps, what injectiveness, what does it mean to be an injective map, just set theoretic stuff, if you have this, you will be fine. This is the minimum that I need. Without use, otherwise you will struggle to follow. So you have this for you to refresh, and pages, these pages here that I've highlighted, that should give you a good indication of this good grasp of these concepts. So, and one of the reference materials also that I will share, one of the topology textbooks will also have a set theory section where you can also refresh yourself. So yeah, so get this. Now, for those of you, especially those guys, who have some analysis, or calculus, you will have more advantage. This is not to say that it's impossible for the others, but it's just if you have like analysis and these things, there are certain concepts that you will be able to construct faster. You will be able to click, boom, like for example, continuity and these things, this type of stuff, things will, especially when we are doing things in abstract, you will be able to see things more concretely, construct stuff much more easily than, if you didn't have any analysis course. But nevertheless, this doesn't mean if you don't have analysis also, that's fine. It's not a thing. If you focus on this, it means that it will be a little bit, you have to work, your brain has to work harder than if you had like, have some background and analysis. In fact, one of the things you will see, the power of topology is a lot of notions that, are very hard to define in analysis will become like, like very easy really to kind of define. The notion of continuity, for instance, you will see what I mean once we get into it actually. So, okay, so someone is taking real analysis. Yes, so this will be very helpful. You will be able, especially when we, not so much in the abstract in this part here, but in here, when we are talking about the metric spaces and the topological space induced by the metric space, you will be in a good position if you are taking real analysis. Okay, so. Likewise, for those of you, if you did some calculus, for instance, when we are talking about differentiable manifolds and these things, a lot of stuff, that you did on Rn, calculus on Rn will become very handy, So, okay, so this is what I need you to, get a grasp on before you you turn up on the 25th of June. Otherwise, you will struggle. Now, the textbooks. This is what I have at the moment. This is really a classic one. James Harmon-Kress. This is like, I think it's one of the first books that I bought online. Yeah, this is really a classic of topology. It has a lot of exercises and so on. So on the topology side, I recommend this. There are other textbooks also you can search and these things. The thing with the books is really there isn't like you have to often try different authors in order for the concepts to think. So don't just stick yourself with the one thing. You can search around. But this is definitely I think on the topology side, on the point set topology side, this is a very good book. And the good thing is I have a PDF version of this, courtesy to one of my colleagues who shared it with you. So I will share a URL with you that have a zip file with the resources with this book and this on PDF for you guys. This one, not really. So, if you want, you can, this is also recommended. It's not necessarily that I'm going to follow all of them because I will have my own style, but, for you like self-study and these things, I definitely recommend these guys. These two, let me share the link actually. For those of you who are here now, you can download the thing, a zip that contains the resource materials. There you go. On the chat, let me know if you have any issues. I'll put this on a test file later and upload it to the thing. I cannot upload the books themselves on the thing on GitHub because you might have like takedown notice and these things. But yeah. So this is the thing for the for this section. Now for the manifold side of things, I'll have this. So let's start with this and see, if you are struggling and these things, I might find other references and these things. But the good thing with this, it doesn't just contain like the basic stuff that we need. It will also be like a reference for more advanced stuff, for us to come back to, in the lead theory section, and even for other topics that some of you, especially those of you, planning to do graduate studies, in mathematical physics and these things, So, it's definitely a reference thing. We will start with this as a reference material. And then if it gets harder with you, maybe I will find other stuff. So this is also contained, these are contained on the thing, on the zip. Okay, don't tell Springer. Okay, so that's it really in terms of the study materials. Before I open up for Q&A, the stuff will be available like not like the reference materials for the lectures and the thing in the crash course will be obviously available here, as you already know. You can also, the video will also be available on YouTube. And I really encourage you also to get into our Gitter community. And one of the things that I will also encourage you, especially in the lead theory section, or even in the crash course, in the summer crash course, is for you guys. I know some of you have like you already have like common communities on Discord and other stuff, but I definitely recommend you coming together to like maybe you could form some study groups amongst yourselves, those who are on the same time zone, this type of stuff, because it will really be very very hard. A lot of the stuff that you will find it easier if you have like especially in trying to prove theorems and this type of stuff. It's always good to have like a companion, so you can bounce ideas and bounce stuff. So okay, so someone is asking, the book by Moncres you share, is it okay for self-study? Yes, it is okay for self-study. Yes. Obviously, in our case, in our crash course, we won't go through everything on the thing on the point set of the stuff. We only need what. In fact, one of the things that I will do on here. Let's go back here. So, what some of the things that I will. One of the strategies I will do. There are some concepts that I could define in the abstract sense. Instead, I won't do that. I will do that in here in this the topology here induced by the metric space. Because otherwise, if you define it here, then you have to repeat ourselves, and it's harder for you to see the concrete, to see like concrete stuff on the abstract sense. So one of the things that I will do is definitely that some concepts, some topological concepts, I will define them here because it's much more easier to see once we think, as opposed to defining them in the thing in the abstract in the thing. We'll define it on the metric thing, on the topological space induced by a metric space. Okay, so now the Q&A is open. I don't know if anyone has Oh, okay. Here's Soham. I will actually invite Soham on the screen to see if Soham, you have to you want to say anything.
Hi. Yeah, I think your plan is pretty good, and it's probably best for people who are just going to learn this to start maybe some sort of early learning by themselves. It'll be much easier to follow the lectures, I believe.
Okay. Yeah, that's why one of the reasons I decided to share the materials ahead, for the curious and the thing, because this is the thing with topology, unlike the algebraic stuff where you can pretty much quickly, see an example because we are used to, topology is, compared to the other branches of mathematics, is, relatively a new subject. It's just over 100 years or so. So, it's very hard to kind of, so it will challenge you a lot in terms of like concrete examples and these things, So, yeah. So in the sense, it's beautiful, but it can be very abstract, There are some, obviously, when we're talking about manifolds and these things, there will be like some stuff that you're already familiar with, like the donuts, the sphere, and this type of stuff. Yeah. So,
Yeah,
but then
yeah,
the problem
exactly.
is the problem is if you are going like for practical stuff when you are going at higher dimensions, right? Where you cannot really draw these things, right? So
Right.
yeah, that's when the abstraction comes. It becomes a little bit harder.
Yeah, yeah, exactly.
Um, Come on, guys, please ask a question. Ask myself or ask Soham himself. He and his friends, physicists, what do they think about Lie theory, about Lie groups in particular?
Oh yeah, those are very important. Like I use them in my uh, work too. So if you and like for most of you who have already have some idea about quantum computing, you must see the SU2 group that comes up pretty often. If you're working with qubits, if you go higher up, like to qubits or qubits or whatever, you will see SU3, SU4 come into play. And if you want to, if any of you plan to do any research in physics, particularly in theory, you will see this kind of groups come up very often. So if you have the idea, then that's extremely helpful, definitely.
Yeah, absolutely. Thank you for emphasizing that. So it's not coming from me, huh? It's coming from our friend Soham, right? So yeah, it's one of those things that often people don't realize. You already been working with Lee stuff without knowing. It's just when you become aware of them, the question is, as you gain more knowledge, what are you going to do with them and these things, and also, you will be able to assess much more advanced literature and this type of stuff as you go along. Yeah. I think one of the things we will do also, we'll see how it goes, especially after we go through these two, try to see the connections with other topics, try to bring in other topics, especially connected to, as close to algebra as possible. We'll try to squeeze as much as possible, maybe Clifford algebras, for instance, these type of things, So, yeah. And then module 2, that's where I think probably, okay, someone is asking a question. Oh, okay, so it's just, yes, the matrix group that we didn't mention the thing, but yeah, they are a canonical example of thing. Yes. So you were already using them without knowing. And you will find some more exciting properties as we go through them. They're very, very interesting stuff. And I hope some of the stuff that I forged on the thing, like the motivational stuff, follow up with them, like, whether in quantum stuff, like the quantum chemistry stuff, but also like deep learning stuff, I find very interesting. So, come on, guys, ask questions, please. Okay, so maybe I can comment something here. Let me go back. I already commented here. I don't want to do that. Let me. Okay, so
I think there is one question.
How deep learning is influenced? Actually, that's why I recommend you to look at this paper, for instance. This guy here. This thing. Give you an idea. But this thing of I think it's all this thing falls into the context of this thing called geometric deep learning, which is a relatively I won't say new, but because it's been around, the idea has been floated around. What would happen if you start considering non-Euclidean, like Riemann manifolds and this type of stuff, learning a manifold. So yeah. Topological data science, for instance. Yeah, actually, you reminded me. Thank you, Soham, for also mentioning topological data science. So, this module, I mean, this. Okay. So this course is a prerequisite. This will not be just for module 2. My company, we actually have plans to do another course, which you are most welcome to attend. I will announce it once we have a fixed date on algebraic topology. So it will be on algebraic topology, and it will be in the context of another course that we plan for probably early next year on topological data analysis. So yes, so actually going through this crash course, you will learn enough about these manifolds and have enough references in order to be able to take the stuff on algebraic topology. In fact, one of the things that I will mention, we'll cover a bit about. I mentioned something on algebraic topology as we go along, because as you will see, classification on pure topological sense is very hard. It's very hard to classify topological objects. So that's one of the nutshell, the motivation around the algebraic topology, because you can attach topological objects to algebraic objects. You attach something, for example, to a group, and then it's easier to prove that two groups are isomorphic in the algebraic sense than proving two topological spaces are homeomorphic. So you will see what all this means. Blah blah blah. Okay. So yeah. Something called there's something called topological Q. Well, I assume it's related. So I assume it's mentioning topological quantum computation. Yeah. I'm not really familiar on the hardware side of it, but I assume it's probably related. So yes, so I'm seeing your other chat, Soham, with the George, the answer, or the decision matrix.
Yeah.
Yeah. So there is a. There you go. So Soham also answered. You want to comment on this about this?
So probably many of you have heard the terms called bosons, like they are some sort of particles. Then there's another group of particles called fermions, and then there's a third group which is actually not a fundamental particle, but more like a quasi particle called anions, and these appear when you make the topological quantum computers. Or I know at present Microsoft is working on topological quantum computing. I don't know exactly what it is that they're doing, but if you uh, there are some nice papers on non-abelian anions, and when you and to understand that theory of anions, which can make this topological quantum computing possible, you will need to understand some amount of Lie algebra uh, for sure for that.
So yeah, so Lee is really omnipresence. Huh? You cannot
Yeah,
escape.
Lee is there everywhere. Yeah.
Okay, thank you. Does anyone else have a question? I have impression there's something else I wanted to comment, but I forgot. I didn't remember because I didn't put it on the slide. It's and then the moment we finish here, I will remember it. Okay, yeah, I have something to say. So for this, I'm planning at least. Sorry. Maybe we'll probably cover. It's possible that we'll cover 20 sessions only, at least, hopefully. I hope.
That's good.
So, and it will be like, hopefully there will be at least one person remaining. If everyone leaves, and then I will stop, okay? So the plan is to do at least 20. So if we get by session 8, if people everyone leaves, then okay, yeah, we'll leave it to session 8. Okay, yeah. Yourself, you have any other question, or any other comment you would like to make, Soham?
No, I think I just look forward to this. I have been also planning to learn representation theory in more detail, so this will also be extremely helpful to me. So yeah, I definitely look forward to this and to interacting with you all, and hopefully I'll be able to answer questions. Though these are more advanced topics, so my knowledge is also less compared to the previous topic.
Yeah, no, I'm sure you will. And we appreciate your invaluable input into the community. So I'm sure everyone, all the guys here, appreciate your interaction, right? It makes it less boring if it's just me, blah blah blah. So let's have someone, especially someone coming from a physics background, right? So to be able, to guide the guys on the chat. So it's really very invaluable help. So thank you so much for that.
Sure.
I have impression maybe people just want to it's been like 45 minutes, so maybe people have other stuff to attend or something. So there's nothing else to be said on this. So I hope for those of you who are just joining, let me paste the link again to download the materials, the reference study for the crash course, and also the manifold section will be more than. Okay, so this thing is telling me that so Crowdcast chat is very smart. So let me just do something, blah blah blah. Okay, yeah. So I added some stars because it was not enabling me to paste the same URL. So for those, yes, I know you are just arriving at the moment. So that's the thing for you to download the reference, the study stuff, the self-study material. So yeah, for those of you, final comment I want to make is I already some submissions for those who want career stuff and also like certification and these things. I haven't had time to review them, but I'll follow up as soon as possible. So yeah. So yeah, I have nothing else to say. Because there are no questions. I assume you have no other questions to ask. So I guess we end here. Unless Soham, you have any final stuff that you would like to say.
No, I think I'm good. Yeah.
Okay, good. So guys, thank you so much again, and I see you on Friday, 25th. It will be very fun.
All right.
Huh?
Yep.
Okay, thank you again.
See you.
Thank you. Okay,
See you.
yeah.
Thank
See you
you.
all. Okay.
Bye.